In this video, we're going to look at some work that is part of tutorial 4. And specifically in this case, we're going to be looking at 9.3, 9.4, and an additional hypothesis test from your study guide, which is the hypothesis test for the population variance, right? Remember, the tutorial 4 is based on 9.1, 9.2, 9.3, 9.4, and as well as the hypothesis test for sigma squared. Okay, so 9.3, you would see that it's concerning your population proportion, right, from your textbook. So now you want to perform a hypothesis test for the population proportion, and remember, proportion is usually some kind of success that you are interested in over the total sample. Okay, so now you have to take into consideration that you will have two cases, right? It's either you have a small sample or a large sample. So in the first case, we consider the large sample, right? And remember, for large samples, as usual, you always use the normal distribution. Okay, so what does a large sample mean? Okay, from previous chapters, remember, because under 8.0 now, you are assuming that the population proportion P is equal to P naught, then your P in this case will be P naught, as the hypothesis test says, right? The null hypothesis says there. Okay, so we say that we have a large sample size if NP naught is greater or equal to 10, and the most important thing is an and, right? So if one of this is not true, then you can't use the standard normal or the normal distribution to perform the hypothesis test. So both NP naught and NQ naught should all be greater or equal to 10. Okay, good. So in a test, you would have to check whether this condition is satisfied or not, so that you know whether you're going to be using case 2 or case 1. So case 2, it will be your binomial distribution, where you are directly modeling the number of successes, okay, using the binomial distribution. Okay, so I'm going to give you an example for large samples. Okay, remember, your test statistic is that it's always p hat minus its expected value, which is p naught, and divided by standard error, which is square root of pq over n. And in this case, because you believe that p is equal to p naught, then you would have p naught into 1 minus p naught over n, right? So let's look at this example. So a machine in a factory must be repaired if it produces more than 10% defectives among the large lot of items that it produces in a day. So the most important thing is it is repaired if it produces more than 10% of these defectives, right? And then they continue. A random sample of 100 items from the day's production contains 15 defectives. The following hypothesis must be tested on a 5% level of significance. Okay, so they were very nice. They give you what is actually the hypothesis there. As always, you believe that this machine must be repaired if it's more than 10%, right? So that's why there your alternative is greater than 0.1 because of more than, okay, right? And then the null hypothesis that P is equal to 0.1. All right, so does this evidence indicate that the machine must be repaired? That's a question you should answer. And when do you repair a machine? As they say there, it is repaired if your alternative appears to hold strong evidence against your null hypothesis, right? So it means that you would say that the machine must be repaired if you reject H0. And if you do not reject, then it might suggest that the machine does not need to be repaired. Okay? So now they say use significance level of 5% and show your steps in testing your hypothesis procedure. All right? So let's start there. All right? So you already know that the null hypothesis is that P is equal to 0.1 versus the alternative that P is the alternative that P is greater than 0.1. Okay, and then now, okay, let's start here. So which case are we using? Are we using case 1 which is the normal, okay, z is normal 0, 1, or are you using case 2, which is the binomial, right? Cool. So remember, we have to check NP naught, which is equal to 100, multiplied by P naught, which is 0.1, because remember, a 10% of 100 is just 10, which is equal to 10, which means it satisfies greater or equal to 10, because there is the equal to there, it's included, right? And now check another, remember, n into 1 minus P naught, which will be equal to 100 multiplied by 0.9. 90% of 100 is just 90, right? Which is greater or equal to 10. So now your statistic, your check, what do you call? The way that you check whether you use a large sample size, all the requirements are met for a large sample size, right? Since you have that your n into 1 minus P naught is greater than 10, and also NP naught is greater than 10, greater or equal to 10, then you can use the large sample case, which is the normal one. So now that means that your test statistic will be given by z is equal to P hat minus P naught over the square root of P naught into 1 minus P naught, all divided by n, okay? And P hat, according to the scenario, remember they said a random sample of 100 items from a day's production contains 15 defectives. So your estimate of your population proportion according to this sample, it will be 15 over 100, right? So there you'll have 15 over 100, okay, minus P naught, which is 0.1, divided by the square root of 0.1 multiplied by 0.9, and you divide by n, which is 100. If you punch everything into your calculator, you should get 1.667, right? So then now remember, we still need to make a decision, so we need our rejection region, right? And remember, this is our rejection region. It will be equal to z such that, okay, so remember you have an upper tilde, so you will reject when the test statistic z is greater than the critical value, which is z of alpha, which is equal to 1.645, because you're dealing with a level of significance of 5%. Okay, right? So now we go and check so that we can make a decision. We see that our test statistic value is 1.667, and this is definitely greater than 1.645, right? So that means that you reject the null hypothesis, right? Okay, and remember, in this question, they specifically rephrased it so that you answer what they said. So you said, does the evidence indicate that the machine must be repaired? That's the question that you are asking. So you should reject or do not reject, but also make a conclusion with regards to what they were asking. Because now remember, like I said before, if we reject 80, right? If we reject 80, it means that we don't have enough evidence to say we do not reject 80. So in this case, we rejected it. So that means we are leaning more onto the alternative, which means that it also suggests that this machine must be repaired according to this. Because remember, the machine is repaired if it produces more than 10% defective. So if you're leaning more onto the alternative, it means that your evidence, your statistical sample or statistical evidence indicates that the machine must be repaired. Okay, so that should be your conclusion at the end. Okay, so now let's move into the calculation of the type 2 error probabilities. And remember that the probability of a type 2 error occurring is the probability of 80 not being rejected, given that it's actually not true. So that means you are favoring the alternative, right? And they gave you the different type 2 error probabilities in your book for different scenarios, right? So this is for an upper-tailed, this is for a lower-tailed, and this is for a two-sided or two-tailed test. So in this case, remember, from example 1, we were looking at an upper case. So our case will be this case, right? So we're going to use this to calculate some example based on example 1 on how to calculate your type 2 error probability. Okay, so I came up with a scenario here. So calculate the probability of making a type 2 error when p is actually equal to 0.2. Okay, so remember, there p prime indicates the value that is part of the alternative. In a way, it's greater than 0.1, in this case 0.2, and you know that 0.2 is definitely greater than 0.1. Okay, so you're going to calculate the type 2 error probability at that point. Okay, so this means that your p prime is equal to 0.2. Okay, and then which case do we use to calculate the probability? Like I said, this one. Okay, so this means that beta of p prime is equal to 0.2 will be this. So it will be p naught minus p prime plus z of alpha multiplied by the square root of p naught into 1 minus p naught. Okay, and you divide this by n. Okay, and then you have to divide the whole thing by the square root of p prime into 1 minus p prime, all divided by n, right? And remember, this function indicates the CDF of a standard normal. Okay, right, so let's substitute the values in, fairly straightforward. So this will be p naught at 0.1, remember, and then your p prime at 0.2 plus your z of alpha, which is 1.645, multiplied by the square root of p naught, which is 0.1. 1 minus p naught is 0.9, and you divide by 100. Okay, and you divide the whole expression by the square root of p prime, which is 0.2, and 1 minus p prime will be 0.8, and you divide by n, which is 100. Okay. Okay. Pressing this into your calculator. So it's 0.1 minus 0.2 plus 1.645 multiplied by square root of 0.1 multiplied by 0.9, all divided by 100, divided by square root of 0.2 multiplied by 0.8 and divided by 100. Okay, so you should get negative 1.27, right? And then if you go to your standard normal tables, this is fairly easy. I'm not going to go to the tables for you, but that should give you 0.102, because I assume that you're very comfortable with using standard normal tables. Okay, so now let's look for a case. Let's look at the case where we have small n. And what is small n? It's when np naught is less than 10, or when and it could also be n, both cases. As long as one of them does not withhold that property of np naught or nq naught being greater or equal to 10, then yeah, you use the small sample, right? In the small sample case, we don't use the normal distribution, or the standard normal rather. We use the binomial distribution, which means we are directly modeling the number of successes, right? Okay, so now I gave you a little bit summary there of this test for the binomial. Okay, so the null hypothesis is the same as always, and the test statistic now changes. The test statistic now is the number of successes. So in our first example, which had to do with the number of defectives, that means that x will be the number of defectives because that's our success, right? And we say this follows a binomial distribution with parameters n and p naught, because under 80, we believe that p is equal to some value, some hypothesized value, p naught. Okay? So as always, you have three alternative cases. You can either have an upper tail test, you can have a lower tail test, or a two-sided or two-tail test. Okay? So one thing that I would suggest is so that you do multiple examples for this binomial case, so that in a test you're used to how to perform a hypothesis test using this situation, because now it gets a little bit complicated and such that now you have to find this value c such that this is true, and this is your type 1 error probability, right, for the upper case, and then for the lower case this is your type 1 error probability. So you have to find this value c such that this is true, and for this case you also have to find this value c such that this is true, where alpha obviously it will be the one that you choose theoretically, so it'll be 5%, 10%. Okay, so now you will go and look for the value of c that satisfies that. Okay, so that will be your critical value. It's very important. So okay, and then for when it's not equal to, then you look for this value c, okay, such that the probability that x is less or equal to c, okay, plus the probability that x is greater or equal to c is less than alpha. Okay. All right, so let's look at an example. So suppose a model car is known to sustain no visible damage 25% of the time in a 16 km/h crash test. Okay, so the most important there is no visible damage of 25%. Okay. So let's continue. A modified bumper design has been proposed in an effort to increase this percentage. To test this, an experiment involving n is equal to 20, you already know it's very small, and this probability is 0.25. So 20 multiplied by 0.25 is definitely going to be less than 10. Okay? If I plug into my calculator, I get 20 multiplied by 25%. 25% of that, which gives me 5, which is less than 10. So already one of the properties of a large sample size is broken, right? So you have to use the binomial. Okay, so now suppose x is the number of crashes with no visible damage, and let p denote the proportion of all 16 km/h crashes with this new bumper that result in no visible damage. So now formulate the appropriate null and alternative hypothesis for the scenario, right? Okay, you already know that the p naught under the null hypothesis, this means that this is your p naught there. P naught is equal to 0.25, okay, under the null hypothesis. Then what about the alternative? Okay, let's read the scenario again. So a modified bumper design has been proposed in an effort to increase this percentage. So to test this experiment, okay, you take a random sample of 20, okay, prototypes of the new design, and suppose that this is that. Okay, so right. Okay, so the modified bumper design has been proposed in an effort to increase this percentage. So we are saying in the alternative that h naught is that p naught is equal to 0.25. Okay, and then the alternative will be, because we're looking to increase that, so p naught is greater than 0.25. Okay, so you kind of just sometimes have to read the scenario 2 times, like I did in my case, to actually find out what is the alternative hypothesis that you're trying to test. Okay, and then let's look at B, which is what our main concentration. So now they say, calculate the exact significance level if the rejection region is given by all values of x greater or equal to 8. Okay, significance level, remember, that's your type 1 error probability, right? Which is defined by alpha and is the probability that height 0 is rejected, right? Given that it is actually true. So you reject the null hypothesis while it's actually true, okay? Or while it's actually not supposed to be rejected, right? So this, remember, then what does it mean for me to reject the null hypothesis? According to this, I'll reject that if x is greater or equal to 8, right? So I will reject it if x is greater or equal to 8 given my null hypothesis. But my null hypothesis is saying that p not is equal to 0.25. So it will be, given p is equal to 0.25. Right? So now remember, probability of A plus probability of B in the same vector space, that's 1. This implies that probability of B is equal to 1 minus probability of A, right? So we're going to apply the same logic. So this will be 1 minus the probability that X, note, less or equal to 7 given P is equal to 0.25. Why? You are dealing with a discrete case, right? So values that are less than 8, it's less or equal to, equivalent to less or equal to 7, because you're not including 8. So you're going to start at 7, okay? You're going to end at 7 rather, okay? So now this means that this is 1 minus, you can read the value from your binomial table of 7. And remember, you had that n is 20 and your p naught is 0.25. So you're going to have to go to the tables and read that value. And if you look at your tables, you see that that value, it's actually 0.898. Okay, so if you press that into your calculator, you get 1 minus 0.898, which is 0.102. Okay, so you've answered that question, right? Okay. So now let's say you were actually, I have another question. So how about, we find out whether we would reject or not reject this hypothesis, okay? So we look at it and we see that we are looking at the upper tail test, okay? So that means our case is this one, right? Okay, so we have to choose this C value such that it's less or equal to alpha, right? Okay, so we have to choose that, okay? And in this case, since we calculated the alpha to be 0.102, we can maybe choose a significance level of 10%, but in a test, there will always be specific on what alpha you should use. In this case, I'm just giving you an example. Choose for alpha is equal to 10%, okay, a significance level, okay? Then we're gonna go to the tables and look for this, such that this is true, all right? So we have to choose C. So you have to choose C such that 1 minus probability of C and, C minus 1, because it's discrete, C minus 1, N and P naught is less or equal to 0.1, right? And this is 1 minus B of C minus 1, and our N is 20 and our P naught is 0.25, okay, must be less than or equal to 0.1. Okay, so if we solve everything else, we see that you should have negative B of C minus 1, so that we can use the tables, 0.25, and then subtract 1 on both sides. Here you have negative 0.9 divided by negative. That means you'll be left with B, C minus 1 of 20 and 0.25, okay? Must be, because you divide it by negative, then the sign will change there. It will become greater or equal to 0.9, okay? So now you have to go to your binomial tables to look for what value, right, satisfies for that. So we will get this. And remember, that means that c minus 1 will be equal to the value that we get from the table, and then we can actually calculate what c is. Okay, so let's go there. Remember, we have n 20 and p not is equal to 0.25. So let's go up. Okay, so these are your binomial tables, and we're looking at n is equal to 20, right? Okay, and we're saying we're looking at 10%, which means alpha is in this case there, right? And we are looking for the critical value. Okay, we're looking for the critical value. So remember, this is the CDF, or yeah, so it's CDF, but it's not the, yeah, it's for, is the, just what do you call, as the, not CDF, I want to find the word in the discrete case, but you know what I mean, the equivalent of your CDF in the discrete case, so the cumulative binomial probabilities, okay? So now you're looking at this case there. Let me rather use, okay, so you'll be looking at this guy there, right? And you're interested in finding what x is, okay? So we are saying that we want this value according to this such that this probability is greater or equal to 0.9, okay? So let's look at that. Where do we see 0.9? 0.9 starts at x is equal to 2, okay, there. So we see it starts, sorry, that's for 0.05. So here, okay, so it starts here from x is equal to 4, right? So we start at x is equal to 4. Okay, so because after that it's greater or equal to, yeah. Okay, so that means that it starts at, okay, oops, sorry. Yes, so you're gonna start there, right? So that means that c minus 1 value, where we start having a probability that is greater or equal to 0.9, it's that, okay? So it means it's 4 there, okay? Right. So now let's continue. That means that this is 4, which implies that C is actually 4 plus 1, okay? Which is 5, right? And then you saw that the number of defective in this case, which is x, what you are interested in, which is your test statistic, it's actually, yeah, in this case, it didn't give you, but let's say maybe maybe they gave you the number so that you can estimate the proportion stuff. The estimate proportion, then you'd be able to make a decision after that, because then you would know Okay, so I'm just showing you how to read off the tables and use this this table there that I provided to perform a hypothesis test for the binomial case. Okay, so now let's move on to the population variance, right? Sigma squared. Same thing, basically hypothesis, null hypothesis testing, and hypothesis testing in general is the same thing. You always have some null hypothesis, you need a test statistic, you need a way on how you are going to reject or not reject the null hypothesis, right? You can either use the confidence interval method or use the critical value method or rejection region, or also use the p-value, which is the last section that we're going to be looking at. All right, so a parameter of interest here at sigma squared, which is your population variance, and we're saying that is equal to some hypothesized value there. Okay, so remember, just note that in your notes, this is y. Okay, so this should be y, that should be y, That should be y, right? According to your lecture videos, okay, and your notes. So that you're not confused. It's the same thing, all right? So the test statistic, remember, that has to do with sigma squared. It's always this one, n minus 1 multiplied by the sample variance squared, multiplied by the sample variance divided by the population variance, right? It's always like that, and it's chi-square n minus 1 distributed, right? And in this case, you have to be careful of how you're going to be, what is your rejection region? What does it look like, right? Because now you're dealing with the chi-square. With the normals and the t's, you would get away with it because now they were symmetric distributions. So it didn't matter whether you can just use alpha, right? And you still get the same thing. But now you have to consider the fact that a chi-square is not symmetric, but rather it's a right skewed kind of distribution. It looks like this, okay? All right. So remember the area to the right, that's our alpha, okay? And there's another there. This one would be 1 minus alpha, right? Okay. So then, this is for an upper tail test. We would reject if our test statistic value, which is y or chi-square there, is greater or equal to this value there, okay? Because it makes sense there, okay? Right, and then for a lower tail test, obviously we'll be looking at this area there. So we reject if this test statistic is less or equal to 1 minus alpha over, with n minus 1 degrees of freedom. So I feel like just draw this plot or this diagram when you perform this hypothesis test for chi-square, so that you don't forget the rejection region, okay? Right, and remember that for a two-sided, then there you'd have alpha over 2, there you'll have alpha over 2. So it'll be 1 minus alpha over 2 and alpha over 2. Okay, let's look at an example. So variability in height is an important factor in determining the suitability of plants for mass displays. The sample standard deviation in height of 81 plants of a new variety of dwarf Zena was 8.7. So note, this is a standard deviation, not the variance, okay? Test the null hypothesis that the standard deviation does not exceed 1.25. So it's important, does not exist. That does not exceed, 7.25. So this means it should be less than or equal to. So you're going to be looking at a lower tailed test. Okay? So you want to calculate that. It does not exceed 7. Oh, sorry, that won't be your alternative because this is saying test the null hypothesis that the standard deviation does not. Okay, so under the null hypothesis, you're saying that 80 in a way, it's informally is not the formal way. It's basically saying sigma is less or equal to some value sigma naught. Okay, so that means that your alternative then will be sigma is greater than sigma naught. Okay, cool. Right, so now you know. So just read the question carefully. Just make sure you read it twice in order for you to get the correct information. As I always say, you see here, I also read it twice again to make sure that actually what I'm saying is true. Okay, so now the figure accepted by Nesriman as the upper limit for the mass displays. Use the p-value approach to reach a conclusion. So, but now I'm not going to use the p-value approach. I'm going to use this p-value approach. I might give you an example of, how to calculate a p-value of the chi-square at the end for the same example. Right. So now let's look at it. So now under 80, like I said, you would have that sigma squared. Remember, this is for sigma. But sigma is related to sigma squared. So if you're testing for sigma squared, you're also testing for sigma as well. So this should be equal to 7.25 squared. Okay. okay? Because they gave you the standard deviation, so you have to square it, right? And then the alternative will be that sigma squared is greater than 7.25 squared. Why? Like I said, they say test the null hypothesis. Under the null hypothesis, you believe that the standard deviation is less or equal to. So the alternative is the opposite. It's strictly greater than. Okay. So now your test statistic, remember, just indicated by TS there. So it'll be y is equal to n minus 1 s squared over sigma naught squared, right? And that would be n minus 1. What was your n? Your n was 81. So n minus 1 will be 80. And then s squared is your sample variance, which is 7. Yeah, which is 8.7, sorry, which is 8.7, okay, squared, because they gave you the standard deviation divided by sigma naught squared, which is 7.25 squared, right? Let's plug that into our calculator. You get 80 minus 8.7 squared over 7.25 squared, which gives you 115.2. Okay, so remember you need a rejection region. So you would reject, because now you're dealing with an upper tail test. If this chi-square, your rejection region is y, if y is greater than chi-square value of, testing at 5%, if I remember. They didn't say, but if they don't say, automatically assume 5%. Okay, so it'll be, because it's upper, it will be 0.05 and 80, okay? And this is approximately equal to 101.8795. So if you go to your tables, you will see that actually this value is not tabulated. So in the test, I assume that the lectures, maybe they're gonna make sure that the value is tabulated, but at the bottom of your tables, they gave you like an approximation. Let me go to your table so that you know what I'm talking about. Okay, so looking for chi-square values. Okay, so you see, they only give it to you up until 40 degrees of freedom, but now we had 80. So you'd use this approximation. So if you put appropriate alpha, which is 0.05, okay, and v is equal to 80 into this formula, you would get this value that I got there, right? Because that's how exactly I got it. Or you can use software, but in a test, you don't use the software, okay? So now, okay, so it will reject if it's greater than that. And we see that this is actually greater than that. So we reject 80, all right? Fine. So now let's move to p-values. So by definition, a p-value is the probability calculated assuming that the null hypothesis is true of obtaining a value of the test statistic at least as contradictory to 80 as the value calculated from the available sample. So a decision, okay? So that's what I was saying, that you can also use the p-value to accept or reject the null hypothesis, which is usually the case, because going to the tables, finding the critical value is a lot of work. So a lot of people just use the p-value approach. It's very easy, right? So it's like you reject the null hypothesis if the p-value is less than alpha, and you do not reject if it's greater than alpha. So you reject if the p-value is less than or equal to alpha, and do not reject if it's strictly greater than alpha. Okay, so in simple terms, a p-value is a measure of how likely it is to get a statistic or something more extreme in the direction of the alternative hypothesis. That means in a way you're favoring the hypothesis over the null hypothesis. Like this, if the null hypothesis is true. Okay, so how likely is it that if you take another sample, your test statistic will be around the value that you calculated now? Okay, all right. So a p-value, let's say for an upper tail test, remember this will be your alpha, right? Your alpha. And let's say your test statistic will be there, right? Your test statistic somewhere there. Then the area to the left there of your test statistic, that's the p-value. Okay? Right. So you can do the other case for two-tailed and for two-sided, and also for lower-tailed. Okay? So now, just gonna calculate the chi-square for the chi-square test, the p-value for example 1. Okay? Remember in example 1, we calculated this test statistic. Let me just remind you. Let's go back up. Right? So we calculated the test statistic to be example 2, sorry, to be 115.2. Okay? So we have that our test statistic okay, and then our alternative, remember, was upper tailed. So your sigma squared is greater than 7.25, if I'm not mistaken, squared. Okay, so I would say the procedure of calculating a p-value is like this. So you have some null hypothesis. Now you calculate the test statistic. Now use that test statistic to obtain the p-value. Okay? Right. Okay. So for an upper tail test, the p-value, it will be the probability that whatever statistic it's greater than the, what do you call, the distribution of your test statistic, it's greater than the test statistic value there. Okay, so it will be, in this case, it will be probability that y is greater than 115.2. Okay, so the p-value is to the right, and then for the other case where the alternative is sigma squared is less than 7.25, that will be a lower tail. The p-value will be at the lower side. So you will be calculating probability that y is less than that value. Now, if it's upper, you calculate that y, or whatever distribution that you're using, or if it's like z, if it's t, it's greater than that value. And if it's lower, you use you calculate the lower probability. Okay, so that means the probability that y is less than 115.2. Okay, and then if you look at that, that would give you so let's go to our tables. Okay, so the chi-square, it gives us the upper tail, so we don't need to transform that into the CDF. So we're looking for alpha of 0.05, right? And we have how many degrees of freedom? So I had 80 degrees of freedom. Yeah, so in this case, it will be 80 degrees of freedom, which means we can't use the table there. We can't use this tables because it's not tabulated in here for 80 degrees of freedom. All right, so in a test, they will always be specific, but that's how I just wanted to make you understand how to get what the test is, what the p-value means essentially. So now you get the idea, right? But you would go and look for that probability concerning this value on the chi-square tables. Okay. So now let's look for another example that is based on a t-test. Remember, t-test is for small samples. So using a standard diet, turkeys grow to mean mass of 4.5 at age 4 months. A sample of 20 turkeys in a small, which were given a special enriched diet, had an average mass of 4.8 after 4 months. So the sample standard deviation was 0.5 kg. So you have this small sample, it's not from the normal, so you have to use the t-distribution. Okay, so now, so let's figure out what is our null hypothesis. So since it has to do with the mean, that means that we are interested in mu, right? Mu equal to something. What is that value? Under the null hypothesis, we are saying that the mean is 4.5, right? Okay, and then what is our alternative? A sample of weight given. Okay, test whether the diet is effectively increasing the mass of the turkey. So increasing means it should be greater than. Okay, so mu is greater than 4.5. Okay, so now our rejection region, because n is small, we will be using a t-test. Okay, n is 20 from an unknown population, so you have to use the t-test. Okay, so that means your rejection region will be when this test statistic t is greater than t of n minus 1, which is 19, okay, and with alpha of 0.05, okay, and if you read that from your table, that should be 1.729, okay, and remember t, it's x bar minus mu naught over s divided by square root of n, right? And this will be, according to their scenario, they gave you x bar there, they said it's 4.8 based on the sample, minus mu naught, which is 4.5, divided by s, right? They gave you the sample standard deviation, which is 0.5, divided by root of n, which is root of 20, okay? And if you plug in that into your calculator, you get 2.683, right? Okay, so but we actually see that 2.683 is greater than that value, than this value, than our critical value there, which is 1.729. Okay, so that means that we reject the null hypothesis. Okay, if you were using the rejection, if you're using the rejection region approach. But now let's use the p-value approach, okay, which is our main thing. So now b, remember p-value, right? Because it's a right tail test, that will be, and cause the probability that y, or the chi-square, is extreme than the test statistic, which is 2.683. Okay, so now for the not chi-square, but t, okay, probability that this t is greater t distribution is 19 degrees of freedom, is greater than 2.683. Okay, and then let's continue. So now you have to go to the tables and look for this. Okay, right, so you go to your tables. If you go to your tables, you can use A5. If you use A5, you will get that p-value is between 0.005 for p-value, okay, and it should be less than 0.01, right? And if you use A7, you get that the p-value should be 0.07, okay, 0.009, okay. There is no relationship that has to exist between the two. Is that just that this one narrows down this interval here, okay? All right. So in either case, this p-value, if it's between 0.005 and 0.001, they're all less than 0.05. Okay, so in any case, you would reject the null hypothesis. Right? This is it from me, and enjoy your tutorial.